All right, maybe we should start with some introductions, and then I'll hand over to James. So for those of you who don't know me, my name is Cormac Purcell. I'm an astronomer at Macquarie University, but I do lots of cross-disciplinary work these days, and I'm part of the steering team here who's organizing the data quest. Emily and Eric, over to you.
Hi, yeah, I'm Eric Dahlstrom.
And I'm Emily.
And background in astronomy and space engineering, and was participated in first couple of years of FDL in the US.
And I have a background in physics and space science as well, mostly on educational space program development and operations.
Thanks. Sarah, do you want to introduce yourself? If you're there still. I think Sarah may have stepped away. Sarah, there you are. Okay.
Good morning. Very quickly, hello. I'm in London. I'm in the FDL Europe team here, and so we've been working to support the team on the other side of the world as we move forward with the data quest. If you forgive me if I disappear, it's early in the morning here, so I will be joined pretty soon by smaller people, so I'll be off video on.
Yep. Okay. Who's up next? M. Waters, is it Mike?
Yes, I'm an end user, so I manage bushfire predictions and intelligence information in South Australia.
Fantastic. Great to have you here. Dale?
I'm Dale Hamilton, professor of computer science at Northwest Nazarene University up near Boise, Idaho in the United States. And my doctoral dissertation that I finished a couple of years ago was the application of artificial intelligence to mapping post-fire effects. Before I came to NNU 7 years ago, I'd worked under a contract with the United States Forest Service and Bureau of Land Management, leading a development team that was working on fire behavior modeling and fire effects modeling, ecological departure, various things like that.
Fantastic.
Cut off, Cormac. You're muted.
Oh, sorry. Christopher, do you want to introduce yourself?
Yeah, my name is Christopher Thaler. I have a strong business background and went back to university in my old age. So I'm working on my PhD in astrophysics. When I went to back to my studies, I realized there's a lot of brilliant research lying in shelves and drawers, which is not utilized. So I set up a company together with Professor Carter to commercialize research. And we then went into Fireball, which is where we're here today. Fireball is a company which provides a lot of services. The main one we will discuss today is an early wildfire detection, assessment, and mapping system.
Okay, thank you. Tim, do you want to add to that?
Yeah, so I'm a long time, actually Fireball started 20 years ago as a company that I founded, and Dale worked for us at one point. We have done fire mapping for 20 years, basically airborne mapping and then briefing to incident management teams. More recently, well, in those 20 years, I built sensors for all kinds of people. And then more recently, we've worked on automated smoke detection and fusing that data with satellite data for early fire detection and then assessment and ongoing tracking of fires.
Great, thanks. There's somebody joined in by phone ending with 119. Do you want to introduce yourself? Okay, maybe they can't hear us. Marta, do you want to do a quick intro as well?
Yes, I'm Marta Yebra. I'm a senior lecturer at the ANU and also an Earth Observation Mission Specialist of the Institute for Space, also at the Australian National University. And I guess for the last about 15 years, I've been working on the use of remote sensing data to support fire management. I think that's it.
Great, thank you. Gonzalo? Maybe they can't hear either. Kate?
Hi, my name is Kate, and I work for Scion in Christchurch, New Zealand. I'm a research technician, and I've been very interested in doing machine learning and computer science. I have an ecological background, but basically data science is sort of the field that I'm getting into, and I've been working with a bit of remote sensing data and also looking at fire spread as viewed from drones and sort of building models of that.
Great, thank you. Joe?
Hi, I'm a lecturer at Murdoch University in Perth. Kind of a boneheaded field person that goes out and measures and counts dead sticks and trees and all that sort of stuff. And more recently, I've been getting into remote sensing, fire severity mapping, trying to understand the dynamics between past fire management and future fuel loads and fire hazard.
Great, thank you. Mark, do you want to introduce yourself? You're muted, sorry.
So hi, I'm Mark Chung. I am an Aussie based in California. I've been working with FDL folks like James and Eric and Emmeline for the past 3 years, mentoring different teams. So astrophysics and solar physics background.
Okay, thanks, Mark. Georgie? Did I mangle your name? Sorry.
That's all right. Georgi or George, both would be fine.
Yep.
I'm Georgi Safronov, Director of Research from Department of Mathematics and Statistics, Macquarie University, Sydney, Australia. So my main research interest in probability and statistics. So I saw the email about machine learning, statistical learning, and here I am here. And specifically in a change point problem, when you need to identify a change in the behavior of the system as soon as possible, for example, when the certain predefined level of, say, probability of the false alarms. So probably that's about it. Thank you.
Great, thank you. And Sood.
Hi, I'm Sood, based at UNSW Canberra. I'm with the Canberra Space Group, interested in analyzing space images as well as applying machine intelligence both on board spacecraft and on data that is obtained to remote sensing on spacecraft.
Great, thanks. And is there anyone that, oh, sorry, Yuri as well? Is there?
Hi, Cormac. Hi, everybody. So yeah, I'm Yuri Shandrik. I'm a postdoctoral fellow at CSIRO, based in Sydney, and I specialize in the application of GIS and remote sensing in natural resource management. So on a day-to-day basis, I develop algorithms to process large volumes of raster and vector data to solve different spatial problems, so such as forest health, bushfire extent, crop yield mapping, that kind of stuff.
Great, thank you. There was one person who dialed in by phone who we didn't get to. I'm not sure if you can hear me. So if your phone number ends with 119, or you're just the only person who's dialed in by phone. So do you want to quickly introduce yourself as well? Okay, perhaps they can't hear. So, okay, so thank you everybody. It's wonderful to see you all. I would like to pass you over to James Parr, the director of FDL, who's going to give us a little overview of the exciting programs that have been happening in the last few years and what FDL actually is. So James, I'll share my screen. Or do you want to share your screen or will I do the slides?
Oh no, you go ahead and yeah, I can start talking. And I wanted to kick off by saying thank you so much for joining. And I realize that people are tuning in from different parts of the world and different time zones, and FDL always relies on the goodwill of people giving their time. So thank you so much for that. And I've just realized that we are recording this, and perhaps we should point that out just for anybody. We tend to create these resources for individuals as sort of briefing tools, and so I imagine the plan with this one is that we'll make this available for people who potentially want to join the Data Quest at some point. And so I hope that's okay. But we should probably mention that at the beginning. The other thing I'd wanted to thank is Cormac and Emily and Eric, the team that really have put this together. They've done a fantastic job, and also pulling together really an extraordinary group of partners, which is really the kind of, if you like, the special sauce behind FDL. And it's the notion that somewhere between academia and the commercial sector and the space business, there's this sort of beautiful sort of synthesis where you can do amazing things. And really that's been the story of FDL. And we like to work on problems that matter. And so we started with planetary defense, so looking at the best way to keep the world safe from asteroids. And since then, we've looked at everything from solar flares all the way through to climate change and other things. So obviously, bushfires was very much on the to-do list, and this is something which personally means a lot to me. You can probably tell I'm a Kiwi, and I remember my dad, who was a bushfire ranger, fighting fires every summer, coming back completely black with soot head to toe, sitting in the bath covered in scrapes and sores, and these are extraordinary difficult challenges. And of course this is something which is only going to get more challenging for us. So we really want to tackle bushfires, or wildfires as our friends in the US call them. It's a global problem, and it's the perfect moment and time to apply space data and machine learning to see if we can make a material difference. I guess the other thing to say about FDL is we believe it is possible to do really impactful work in a very short period of time, and that's sort of the special sauce. Is we essentially set teams up for success. We provide all the data, we do everything we can, we build a great mentor community around the projects, and then we show that actually the ability to make machine learning pipelines, if you like, the middle of a project, can be done in a very rapid time envelope. And we've proven this. We've, for example, had the best paper at the climate change workshop at NeurIPS, which, if you are a machine learning geek, you'll know that's the Oscars of machine learning. And getting best paper at the climate workshop's a bit like getting the best film, if that's a good analogy. So as I said, we've been looking at planetary defense, space resources, so going back to the moon, space weather, exoplanets, astrobiology, and Earth sensing, climate change. And do you want to go to the next slide, Cormac? And again, I've sort of described the model, but it came back from, if you know this this painting, this is Island 1, which was conceived by a team in the summer at NASA Ames, led by a Princeton professor called Gerard O'Neill. And if you've seen the movie Interstellar, you'll have seen a CG version of this. But this was, again, conceived in a very short period of time over the summer by a group of young people at NASA Ames in Silicon Valley. And this is really to say that it is possible to do extraordinary work in a short period of time if you give people the right ingredients. And do you want to go to the next slide, please, Cormac? And the other thing which is probably worth mentioning is that we obviously we're based in machine learning. This is where we live. We started in supervised learning, which is of course where everybody starts off, but we're migrating into unsupervised Bayesian and probabilistic methods, and we built a really strong community of mentors around those tools, and data fusion, which, if you like, I sort of believe is the sort of unspoken amplifier of machine learning projects. This incredible ability for these tools to synthesize multiple data sets, sort of far beyond the ability of the human human capacity to conceive, and that actually this is sort of like where machine learning comes into its own. So brilliant minds, big questions, and then perhaps go to the next slide. And then this was really an overview of where we've been over the last 5 years, and I'm really thrilled that Mark's here as well, because the sort of bottom right hand of this picture, the Living with the Star, this is much of his handiwork, and he's really helped us flesh out a lot of really significant progress in helping apply machine learning to heliophysics. But as you can see, we've also done work in planetary defense and astronaut health and lunar and Earth. But this chart really shows that we're interested in impact, and this is what the color coding is showing. We're interested in deployed AIs, we're interested in published research, we're interested in enhanced data products and tools, and also startups. And we're learning how to do this better. We have a sort of great exhaust of published papers, and this is something which FDL's got very good at. We're also getting really good at creating really useful pre-processed and enhanced data products for the community. And I imagine that's sort of why, or sort of the end goal of the Data Quest, which is one of the reasons why it's called Data Quest. Do you want to go to the next slide? So a new mode of applied research, which I think hopefully that's the light bulb's gone off for you and you sort of understand the gist of it. And then perhaps the next one, Cormac. And then just to say that we are looking to build the capacity to do FTL in Australasia. There's a program with in partnership with NASA, which is based in Silicon Valley with NASA Ames. These projects I've been talking about last 8 weeks. There's also a FTL in partnership with ESA that's in Oxford in the United Kingdom. And these are independently financed. I should mention that that's completely separate, even though we share methodologies and faculty. And then our aspiration is to build one in Australasia, but we're starting small. We're putting a toe in the water, but we're thrilled to have the Australian Space Agency and the Office of Chief Scientist and Engineer from NSW helping to get that going. So with that, I'll hand it back to Cormac, but I just wanted to say thank you so much for joining. Thanks for Dale, Christopher, and Martha, who's going to take us through some of the science and some of the questions. And I'll give it back to you, Cormac.
Okay, thank you very much, James. So just to make another point on this slide, the larger FDL sprints that happen in the US and in Europe, they're intensively, the teams intensively work through the 8 weeks, but there are enormous resources that go into both the preparation and the deployment and development after the 8-week sprints. So one of the most important things that happens is that there's a challenge definition meeting called the Big Think. And this selects the questions that are both at the cutting edge and are able to be tackled within the 8-week sprint by particular teams. We don't want the teams to spend half of their 8 weeks preparing data and figuring out how things might actually work. So there's a lot of background work that goes into getting the data sets ready for machine learning. And I'm sure those of you who have a machine learning background or have been dabbling in it know that this is almost 90% of the time often of your actual work sitting at a computer. So we want to do the same thing, but on a smaller scale for the Data Quest here. We're engaging our partners who are supplying compute. This is Doug, a company specializing in compute and Earth observations. And we're building a compute environment that everybody can log on to. And we'll be engaging all of our experts to help us get the data sets and put them into a machine learning ready form. And then a couple of weeks out from the sprint, teams will start to engage at a lower level and get used to the compute environment, and then build up to the full week of full-time work where they'll be able to take a running leap at the sprint itself. We'll also provide support for part-time work for a few weeks afterwards. So Imagine that the sprint comes out with a great new method of data fusion. You have a prototype, you've been using it or deploying it, or you've been using a smallish data set to test it, but you want to scale this. And so we really want this to be a useful thing for people to take forward. And we plan on supporting teams to go forward with that for a few weeks too. So the sprint this year, the Data Quest, it'll be in August, towards the middle of August. It's conducted online, like all of FDL. So the normal FDLs in previous years have been co-located at Silicon Valley and Oxford, but everything has moved online this year because of COVID. And so it's a little bit of an experiment for all of us, but we think it's going to work really, really well. There will be 4 teams working on different aspects of the wildfires problems, but we hope that they're working on interlocked problems, addressing questions that use the same data sets.
Can you not hear me at all?
Sorry, was there a question there? No, okay. So yeah, I'll just go on to the next slide there. So this is the general timeline that we'll have for the actual sprints. So teams will start to engage and log into the compute environments on the 27th of July and start preparing and getting used to the data sets and exploring the tools up until the 6th of August. And then from the Friday right through to the following week on the 14th, they'll have 7 days of hard work supported by our experts. So we'll have experts in fires, experts in machine learning, and experts in Earth observations who will be logging on and off and advising each of the teams on a very one-to-one basis. And then we'll have another couple of weeks of low-level support where we hope the teams will continue to engage. Okay, so this is how it kind of looks. So we'll have everybody working, and then the week, and then the 2 weeks after that. So I can send on these slides a little later on. I'd like to hand over to the 3 experts who've agreed to have a chat with you about the questions. So we've selected 3 different challenge areas that we would like to build our challenges around. Now, in a little over a week's time, we'll be bringing experts together to decide on the exact challenge questions that the teams would like to, we'd like our teams to focus on. But for the moment, I'd like to get our challenge experts to set the scene. The 3 different areas are 1, improved fuels assessment. So how can we use satellites and ground-based cameras and LiDAR and other data sets to look at the buildup of fuel on our land? The second is early detection, so finding fires as soon as they start. And then the third is how can we make sure we know where the fires are going and what they actually do? And can we use machine learning to bootstrap that in a much better way than we currently do? So Marta was going to speak about this. Marta, are you ready there?
Yes, I am. Thank you for the introduction. Yes.
Thank you.
Okay. Can you hear me well?
Yes. Yeah, we can hear you.
Okay. Yeah. Okay. So well, probably I don't need to say that a better estimation of a spatial and temporal variation of fire danger conditions is critical for fire prevention. And their fuel moisture content, structure, and load are all critical factors of fuel flammability, and therefore are essential to assess bushfire danger or to predict how easy a fire will ignite and spread. That is critical in preparing and responding to bushfire events. So around this broad topic, I have identified a few challenges that I have come myself into them after being working on this field for a very long time, also very much involved with the end users via the Bushfire and Natural Hazard CRC project I lead. And one of the challenges is that for this kind of information, the temporal dimension is critical. And therefore, most of the current products that have been developed have been using mainly high temporal resolution imagery. like MODIS or NOAA, AVHRR or vegetation that are again very frequent but low spatial resolution. And there's a need to go into higher spatial resolution products that are needed for certain fire management applications, such as finding differentials in fuel moisture content in different aspects of a topographic feature and things like that. And therefore, when it comes to applied algorithms to higher spatial resolution, especially if we are talking at a continental scale for Australia, one of the challenges we need to come up with alternative methodologies for computing these variables that can provide up-to-date estimations at the same time that are reducing the requirement for storage and computing resources. So again, as we go into having information more frequent and at a higher resolution, then the computing resources and the required storage can be a challenge. So again, one of the things that one of the teams could be using artificial intelligence is to find alternative methodologies for using this information more and computing the algorithms more efficiently. So other of the challenges that there are in this field, and this is potentially more specific for fuel moisture content, is that we don't have still a good model to predict fuel moisture content in a multi-layer forest. So most of the algorithms that currently exist to estimate moisture content are based on optical data, and therefore in a very close forest, they only estimate moisture content of the canopy, because obviously the data cannot penetrate that canopy. So there's a need for the land managers to have also information about the near surface fuel, because the fires normally start on the ground. So there's a need to establish new algorithms that perhaps integrate different data coming from different sensors or different platforms to come up with an integrated value of fuel moisture content that it represents the values for different layers in the forest, basically. And this basically touches the other challenge I said about the better integration of data sources. Because, yeah, so one of, yeah, again, it's what I said. There's a need to integrate different data sources to get the most of its data sources in terms of spatial, temporal, resolution, the capability of that sensor to penetrate the information of that sensor to penetrate the canopies and things like that. And then also most of the algorithms that currently exist produce, in the best case, near-term information, but there is not yet any algorithm that is able to forecast fuel condition into the future. So perhaps there is opportunity to develop some algorithms using perhaps weather forecast to forecast how the fuel is going to look into the future. And that's in terms of improving the information about the fuel condition. But then there is another need into do a better use of this information. So again, as we begin to have more detailed data, then some of the existing models cannot utilize this data. So most of the operational fire simulation models are based on point rate of spread models that were developed long ago. And so they are not able to directly utilize this detailed spatial information. So these models need to be improved to better be able to incorporate this information, or perhaps another approach will be to indeed develop these new fire behavior models, fitting these models to the data that the spatial data that is developed from the arrive from the satellites and sensors. So that's the overview. I hope I didn't go too quickly around it.
No, that's absolutely great. Just one question from me, Marta. Have you got a sense of what problems could be tackled in a 1 week research sprint like ours?
Yeah, I think in 1 week, yes.
Yeah, with
well,
a
I
little
think,
bit of support on the end,
yeah.
on either side.
I think all of them could be tackled, perhaps not fully, but components of each of these problems could be tackled to make a way forward. So yeah, I think any of those topics could be tackled. But probably the more realistic perhaps is in the first problem in terms of better methodologies to make better use of high spatial resolution imagery. That's something that is quite realistic.
Okay.
But
great.
I think most of them could be tackled. Perhaps the forecast capabilities a bit tricky.
Yep. Marta, will you be able to stick around for questions after this in about 10-15 minutes? Will you be still
Yes.
online? Yeah.
Yeah. If my kids are entertained, yes.
Okay, great. Thank you. Okay, so maybe we'll move on to Christopher Tyler. Chris, did you have your own slides to share?
You're muted, Christoph.
I'm muted as usual. No, not as usual.
No, that's unusual.
Okay, if you give me the screen, good. So I just get okay. So here we are. Can you see it?
It's just black. It's coming on. There we go. I can see it. Yes.
Okay. For us, bushfires and wildfires are really close to home. You see this fire front here is about 50 meters from our office. That's Mount Coulomb here, that Parisian beach that was last September. We were evacuated and couldn't go back 2 weeks in our office. Fireball is in a collaboration with all the many logos you see here on these screens, where we tried, or we working, actually we have succeeded to provide an early wildfire detection system, which is already put up in California and is implemented there. I go to the next one. What we are doing is we have, as I said, as a commercial entity, a wildfire detection, assessment and mapping system in place, which uses satellite data and fuses that with ground-based sensor data to determine when a fire starts and give information as early as 3 minutes after the fire ignited to the emergency services. As I said, this is already up and running and tested. We're also working on wildfire prediction model services, where we go a little bit on a low level, and I think Tim can say to that a little bit more a little bit later. We have a wide range of remote sensing applications, where we use sensor hardware which we develop ourselves, where we have wavelength from ultraviolet to thermal infrared, and we use it on several platforms and altitude, such as drones, airplanes, low Earth orbit satellites, and geo satellites. We are working on our own geo satellite right now, which should be launched in 2024, 2025 as a payload, hosted payload on a communication satellite. And we're also working on a satellite constellation where we are involved with Marta and discussing if they want to put their sensors on our payload. Our projects are wide-ranging. So we do not only wildfire detection, assessment, and mapping. We also do mapping of underground coal fires, power line monitoring. We have hardware support on Mars. So we did topographic mapping of the Martian terrain, which was used for the InSight lander to determine where it should land to launch his seismograph instrument. We are also providing airborne sensors for the International Narcotic and Law Enforcement Agency, especially in the Merida initiative in Mexico, which is targeting drug production and distribution. We are involved in that. We did mapping of the North and South Pole. We did topographic mapping of the ice for NASA. And we, of course, work for US Fish and Wildlife service in sensor and survey operations. So now that quick overview of our customers. But what we are doing is right now, if a wildfire breaks out, it's someone sees it, he calls it in, and then it goes to in Australia to the center in the capital city. They inform the local center. Here in our area, it would be Caloundra, and they inform the rural fire brigade, and the rural fire brigade goes out to the fire. And still, at this stage, we don't know what is the fire, how big is the fire, and we don't even know where the fire exactly is. And the rural fire brigade's first task is to do an assessment. And you can imagine that the time from the fire starting to the assessment is very, very long. What we want to do is, and what we are doing is, we want to reduce this time. So we use satellite assets combined with machine learning, artificial intelligence, and ground-based sensors to automatically detect fires, provide the information to the fire emergency services, which then can assess the fires directly on a screen, make an assessment, and send out the firefighting sources. So now I go a little bit further down to get some examples of what we have done and how it's working, but I don't have the time to go into detail to that. What I wanted to show you is how artificial intelligence works. So what I have here is an example from a fire in San Diego. It was the Black Mountain fire last August, and our machine learning system, how it works. So what we see here is an image which is taken by one of the HP RAN cameras. And you see in this purple square that is a little smoke, that is when the fire starts. The machine learning algorithm, it doesn't detect anything, but a minute later, the machine learning says, oh, there's something going on. There's a 1% chance that there's a fire. And then it goes up to 26% a minute later. And after 3 minutes, it says, yes, there is a fire. So I want to hand over to Tim, who gives you a little bit more technical background to that. Tim, you're surprised I will not say anything.
Yeah, so the deep learning system has been trained with, it's got about 80,000 images in it, and we're in the process of building a second deep learning model that's going to be run in parallel to this, as well as a number of, the structure of the model is such that we can move different filters in at different times without disturbing the workflow through the model. So, and it is true that one of the biggest problems with doing a system like this is the potential for a large number of false alarms. We've been pretty successful. We're not at all satisfied with what we've got, but essentially we're getting about a half of false alarm per camera per day. So it takes about every other day there's a false alarm for each camera. But in California, there's almost 1,000 cameras. And that's way too many false alarms for the agencies to be happy with. So we're in the process of a variety of tests for a number of different approaches. And those things range from the different models that we have, the different ways we've trained it, to a number of heuristic and direct image processing capabilities that keep the false alarm rate down. And our stated goal is one false alarm out of 3 million pictures. And for some of the cameras, we get a picture every 10 seconds. So that would amount to about 15 false alarms per day in the whole state of California, which is a pretty acceptable number, given that it's about 1,000 kilometer by 1,000 kilometer area that we're dealing with. You're muted, Cormac.
Yep. So just to ask you both, in the context of a 1 week sprint, and you know, focusing on getting some new research out of this, where do you think the major problems are, and what could be tackled, especially in the Australian context?
Yeah, one of the things that we've been successful in moving between camera systems. Essentially, we've shown on a couple of occasions that we can train in one camera system and then move to another. in sort of different environments, but that's not really totally vetted. So one thing that needs to be done is to move part of the system to Australia. We are going to be putting up some cameras, and it would be very interesting to make sure that the system works as well in Australia as it does in California. So that's one aspect of it. The other one is, a typical false alarm in the San Diego area, for example, which is where we first trained the data, is coastal fog. Okay, so we've put an enormous amount of work into coastal fog, but that doesn't mean that we've captured all sorts of false positives you might get in Australia, right? So you really don't know what kind of problems you're going to come up against until you get to a particular environment. So the challenge then becomes both the basic training set, and then other ways that you can either improve the deep learning or add to the deep learning to make the whole system work together. What you really have to have is a very efficient, high-speed system. For when you have 1,000 cameras and you have a goal of getting an alarm out in 3 minutes, you really have to pump the data through there. So it's fun and interesting exercise. We've been really excited by our results. It looks really good.
And so really, in a little over a week at the little thing we're running, we'll have to identify data sets and problems that we could potentially tackle within.
Right. And we can give we have a lot of data. We've got a ton of data. And in fact, it's difficult to get training sets, but it's also difficult to sort through 6 months of data at an image every 10 seconds from 1,000 cameras. So good ways to screen data that you haven't processed before from cameras that you haven't used before is an interesting problem.
Okay. All right. Well, we're running out of time soon, so thank you very much, both of you, for that. I just want to move over to Dale, who is going to talk about machine learning on fire behavior models.
Thanks, Cormac. So when I started working with, or came to Northwest Nazarene University, started working on my PhD, continuing the work that I've been doing on fire behavior, one of the questions I asked, did a quick survey around campus with a variety of people, and Idaho is an area where wildland fire is a very prevalent issue that we have to deal with a lot. And I started asking people, so if I say fire severity, what do you think? And one of the things that surprised me was it was pretty evenly split between people thinking about an active fire and flame lengths and the intensity, the rate of spread that Marta was talking about, but then also looking at it afterwards and saying, okay, what effect did the fire have on the ecosystem? There was also a small group that we're also looking at as a fire potential of saying as here in the United States, when you go into the wildlands, quite often you'll see signs that are saying, giving an indication of, so are we looking, is this, low, medium, high, very high, extreme, just so we know how careful we need to be out there. So looking at fire behavior, looking at from, what is the actual fire doing? Marta did a great job of talking about the primary things that we look at. So rate of spread, how fast the fire is moving is a big indicator and is a huge issue for looking at firefighter safety. Obviously, a very fast moving fire is a fire that can very quickly catch unsuspecting wildland firefighters and get them into a very bad situation very quickly. Marta had talked about a fire intensity. One of the other ways of looking at that is I look at the picture that we have right next to us is the larger the flame is, the more BTUs being put off, the more energy being released. A third one that she also talked about a little bit also is saying what is happening with the canopy. In the situations where you have a canopy. Right down where I live, here in the Boise area, it's high desert, so we have a lot of sagebrush. So there, pretty much everything's running along the along the ground. Again, herbaceous and the sagebrush. But as we go a couple hours north of here up into the mountains and we get into pine and fir forests, we start getting into different types of fire where it actually looks more like what we have in this picture here, where it may be just going across, the surface and not getting into the canopy, or you may have individual trees that the crown is igniting on, which here in the United States we refer to as a passive crown fire, or it may be a full crown fire where all of the trees in the canopy are, the crowns of all of them are igniting. So when we look at that, as far as what is what is the brush fire doing, if we take a look at the other side of what people were talking about of what was the effect, there's 4 areas that we can look at, but 3 that will be of interest to us. One is what happened with consumption on the ground, the biomass consumption. Another thing that we can look at is how deep into the soil did it heat the soil, and that's going to have an issue on the biotics, on seeing what's going to happen with the seed beds, with vegetation coming back and mortality of certain types of trees. But then we also have tree mortality is another area of post-fire effects that we would look at to see of the trees in the canopy, how many of them were killed either directly from ignition, or also if the surface fire going underneath was hot enough that even if it didn't burn it, it may have scorched it enough, and it'll vary species by species of how much of a crown can get scorched and turn brown before it's going to kill the tree. Some trees are very resilient. You can scorch a third or a half of the canopy and it'll come back. Others, if they see fire, they're gonna die. So looking at those 2 things, both the fire effects and the fire behavior of what is active fire doing, and the fire effects, what happened in the ecosystem, I think are things that we can look at when we say, when we look at what capabilities do we have available to us now that we maybe didn't have available to us when I started working with this about 20 years ago. So as I started working with this, about the time I worked for a summer with Tim, and then started working under contract with the Fire Sciences Lab in Missoula, Montana, with the U.S. Forest Service, and then with other organizations in the U.S. Forest Service and the BLM. One of the things that I see is we have commonly the models that we're using now were created in the 1970s, 1980s, back when artificial intelligence was something that was purely science fiction. 20 years has significantly changed things. We have capabilities now, both algorithmically of developments of new things that have come out in the last 20 years, and also in computing power. One of the big things that's driven the acceptance and the ability of AI to actually deliver on things that were being promised when I was a kid, is because of Moore's law, where every 18 months computers will double in power. So now we have the ability to actually the computing power, especially with cloud computing, to actually be able to run these computing models. The other thing that we have is we're getting to the point now with programs like the Landsat satellites and those of, we have 40 years of satellite data, which was a huge thing. When I first started working with this, around 2000, as we were looking at fire frequency and those sorts of things, and we're looking at the amount of data, one of the things that managers kept coming back was saying, we don't have enough spatial data to be able to tell what's been happening, because we don't even, unless it's an extremely quick fire return interval, we don't have enough data. Well, now instead of having 15 years of data, now we have 40 years of data. And beyond having the data of Landsat, we're starting to which is 30 meter, we're starting to get the Sentinel data, which is 10 meter data or 15 meter data from European Space Agency. There are our private companies, Worldview, where we're getting down close to a meter. One of the things with my research that we found is because I deal with mapping wildland fire using hyperspatial 5-centimeter drone imagery, one of the things that we were able to find was not just from what we saw in the literature of accuracy goes up when your spatial resolution goes down. Jumping from the literature I'd seen, looking at 30 meter Landsat versus Spot, was you jump down to 5 centimeters. And your accuracy just goes through the roof as far as being able to accurately model and map the effects of wildland fire. So
Dale, and just really quick, because we're running out of time.
Yes.
Can you pick a key thing that you might do for a 1 week sprint over here?
I think one of the things for a 1 week sprint that I would be looking at is going back and looking at the fire effects, either the fire effects of what happened, what can we kind of almost from a forensic standpoint look at, say what happened with a fire. We have a lot more data than we used to on perimeters, on severity, pull all that in. What's been collected by the fire ecologists, what's been collected, what we can get from the satellite data, even from the very high satellite data, and start using that to allow us to use machine learning to learn from that data and give us better predictions of looking at the past. Off of that, use that to train those models to better predict what will happen in the future.
Okay, great. Thank you very, very much. Okay, I'm conscious that we're kind of starting to approach the end of the hour. Thank you all for your fantastic summary of the state of the art at the moment. I'm going to go over to Emmeline, who's going to talk about applications for the Data Quest.
Yeah, thanks, Cormac. So I'm conscious of the time, so I'm just gonna quickly summarize the application procedures and processes at the moment. And again, most of this information is actually on the website already, including the actual application form. So our focus here is the goal is to be able to find like four teams of 4 individuals each to actually go through the actual program. And so what we're looking for is a team that is a minimum of 2 to a maximum of 4. And the intention here is to actually find either postdoctoral or graduate level individuals that either have machine learning or AI expertise or domain expertise in bushfire or both. So we call them hybrids. In terms of the actual requirements for applying, we are looking at Australian and New Zealand residents, because even though this is an online program, it is really going to be intensive and full-time, so that we want to make sure that all of the applicants are kind of like within the same time zone. The other thing as well, in terms of the major requirements for applying, is that, so we're looking for, you need the CV for each of the team members. Then there's also the team reference, which a reference for the entire team, and preferably the referee knows all of the individual members of the team and can vouch for their experience working together. There's also a 500-word description of your interest and your participation, and then also a 300-word description of evidence that you have actually worked together. I think, and then as well, so the application is open right now, and it will end by June 1st. And we're gonna try and mix and match as well those teams that do not have the full 4 member teams, and then expect to be interviewed as well once we get to the short list, before we actually finally announce the 4 teams on the 22nd of June. So I think I'll just end there, and let's just go to Q&A if there are questions from people.
I got a question. Do you let the teams choose the topics, or do you sort of assign them to the topics?
I can take that question. So we will be setting the exact questions that will be dealt with at the Little Think meeting on the 14th. And then the teams will be matched to those topics. So we'll be choosing the teams with those topics in mind. So the teams don't really have any scope for proposing a question.
Right, okay.
But do they know the topics before, so they can prepare their applications if they have a preference on a topic?
Yeah, so we'll hopefully have a set of topics after a couple of weeks from now, and we'll be posting those. Well, I guess we'll sort of we haven't thought quite that far ahead yet, but we'll be posting those to the website. So currently we have the basic themes, and after that we'll put the topic, the defined topics on. But really we'll be making the choice on the teams based on previous experience and the sort of rounded view of how a person and a team looks.
So ways we can help Cormac or help you define those questions. That probably is one of the most important things, it seems.
Yes, and we'll be sending around to our research partners. We'll be sending around an invite to our Little Think meeting on the afternoon of the 14th in the next 24 hours, and that's when we'll all come together and decide on what the actual questions will actually be. So,
and the researchers. There's going to be a little flexibility, but in the full FDL 8 weeks, they have more flexibility to examine different approaches, whereas in this 1 week period, it's really the time constraint forces more constraints on this.
Cormac, are we at the point of advertising? Are we going to advertise what type of data and the format of the data we have for each question?
Not yet, because that's going to be an ongoing process. It's going to take, I guess, it's sort of a couple of months really to understand what data sets we can use and to understand what data sets we can get onto the compute environment that we have. So once we've gone through the Little Think process and have decided on our questions, as part of that, we'll be assessing what data sets are available, and then assessing what data sets we can process in enough time to conduct our sprint. So we can release that information later on, but I haven't got a firm timescale yet. Okay. Any other questions from anybody? Dale?
Yeah, I have a quick one, Cormac. So I'm really looking forward to learning a lot about Australian ecology and Australian fire ecology in particular. Is the emphasis of this going to be Australian specific, or are we looking internationally?
The emphasis at the moment is Australian specific.
Okay. That's great. I got no problem with that. Just wanted to clarify that.
Yeah, if we can make it some nice data sets or tools or algorithms which are applicable more generally, that would be fantastic. But our research partners and our funders probably want a little bit more on the ground outcomes here. So we're engaging with people like AFAC Predictive Services and others who are more close to the actual work, and we want them to have a good outcome as well.
No, it makes perfect sense. I just wanted to clarify that.
I just have a question with regards to those photographs of the plumes. I was wondering, apart from the plumes, the other interfering factors such as clouds and mist or fog, are those data labeled?
Yeah, that's in one model they are, in one model they're not, actually.
So how much of the false positive factors are labeled? Is it
Okay, after, yeah, it's interesting. After the initial training of the model, the thing that really improved the model was the teaching of the false positives, teaching not fire, right? Which is really cool. I mean, machine learning is really one of the venues in which, one of the frameworks in which you can really teach the negative. And it does turn out to be really powerful. So that's, yeah, that's really the main way we have, we got last year's model to be as good as it is. And it's turned out to be really good. Right now we're getting about, we had 4 false alarms today in the whole system, which is pretty astounding.
Do you think we can extend this this study for space-based images and push back the detection of the plumes?
Yeah, it's not, well, the ground-based sensors are going to be faster than the space-based sensors, but they're not that much faster. In fact, Christoph, you want to bring the Kincaid fire up?
I think we're almost out of time, so maybe I'll get Sud and
yeah, we should talk.
We should talk offline.
Yeah, it's really good because they're both fast and they fuse really nicely.
Can I go to James and ask you to do some closing remarks, please?
Thanks, Cormac. And I'm so thrilled that getting this, I don't know if firepower is the right word, together. You know, this is why, you know, we do FTL and I get really excited when I hear conversations like we've had today. And I think, you know, it's you'll find that FTL is a big family. And there's lots of friends across the world that have emerged from working on these challenges together. And I just wanted to say welcome to the community. Get engaged. There'll be sprints running in the US and in Europe, and of course you're all welcome to you know, be part of that as well. And yeah, just thanks for your time. And we're looking forward to some really great science and some great thinking over the next few months.
Okay, thank you everybody. Sorry, was there some other question for you? No. Okay, well, thanks everybody. We're available over email as well. If you send questions into the DataQuest email, we're happy to answer those. And if you need extra help or need to chat, we can always arrange another Zoom meeting. There will be, after the Little Think meeting, which is on the 14th, we will have another one of these briefings on the 21st, and we'll have more of an idea of what the questions will be then. And so we'll be able to tell you not just an overview, but much more specifics as well.